So if you look up here on the screen, I have some examples of what we're about to do. These are things that you're going to see. Actually, standardized testing loves these types of examples. All right. Basically completing the pattern. If I say 4, then 8, then 16, what do you think is the next logical number here? 32, because it's doubling, right? 4 doubles, you get 8. 8 doubles, you get 16. 6 doubles, you get 32. They don't always have to be numeric. Red, white, and what is your first thought? Blue, right? Red, white, and blue. Of course, that would be here that you would potentially say that. What about 2, then 4? This is a very short pattern. Yeah, it could be either 6 or 8. That is the answer. So it could be that they're just going up by 2s. It could be that they're doubling it. So sometimes 2 different people can see 2 different patterns when you do in this type of reasoning. Monday, Tuesday, what do you think they're going to say next? Wednesday. All right, and so these are examples of just pattern recognition, and then you logically came up with some type of answer as to what it would be next. This is the process of inductive reasoning. Inductive reasoning is your first definition here, and this is the process of coming to a general conclusion by finding a pattern in several specific examples. All right? Some professions that use inductive reasoning, the weather, all right? They have looked at patterns over and over and over, all right? And so based on the patterns that they have seen, they predict what the next thing will do. If you have ever, however, watched a hurricane, you will know that inductive reasoning does not come to a conclusion. Inductive reasoning comes to what's called a conjecture. A conclusion means that it is definite and it will happen. Conjecture does not. Conjecture is the conclusion that is reached using inductive reasoning. We give it a different name because conclusion we typically use when we say we've done deductive reasoning. What we come to when we do inductive is a conclusion called a conjecture. Okay? It's not always true, and if you've ever watched the weather, you know that's the fact, right? They base it off of a pattern, but the truth is a pattern can change, okay? Patterns can change. So when we use inductive reasoning, we are just doing the best possible answer for what we have been given. The example on the what we just did, we said, it could be 6 or it could be 8. Because based on what we have, the information that we have so far, it could be either. Now, if the pattern had kept going, maybe it would have been more definite. And we maybe would have seen that what it was for sure. But based on what they gave us, the pattern was not exactly conclusive. All right? And so conjecture is just a better representation or a better word when it comes to inductive reasoning, because that conclusion that we have supposedly come to could be different based on some more information that we have been giving. We are basing it off of patterns, and patterns can change. All right? I will say that even doctors use inductive reasoning, right? They'll take symptoms, right? And then they'll go down this path to check something, and they'll say, we'll see if it could be this, because based on these symptoms, here it is. And then they may go down that path and see, no, that wasn't the right thing. Let's go somewhere else and see what else it could be. And so inductive reasoning is used all over. All right? On your handout, you have several examples. The first example is this one that they have given you, 38, 31, 24, 17. So based on this particular thing, what do you think is happening here? It looks like they are subtracting 7, right? And so based on this, if you had to fill out the rest of this, you would keep going with that particular pattern. You would say, well, 17 minus 7, and then 10 minus 7, right? And then we would just keep going as far as you want. That would be the pattern. The conjecture is you're going to tell me how you get from one term to the next. So when I say your conjecture, I want this in words. I want you to say, to get the next term, subtract 7 from the previous term. So your conjecture here is you verbally telling me how you came up to this process, all right? This is really important when you do a quiz or a test, because I have given patterns before that I thought were definite, and then I've had other students find different patterns in it. And so it's very important that you speak and tell what your pattern is and how you did it. So you would just say, to get to the next term, then you would say subtract 7. from the previous term, okay? And that is your conjecture. That would be your conjecture there. Books. So in your books on page 54, patterns do not always have to be numeric. They do not always have to be digits. They can be pictures. They can be pictorial. And I will tell you, standardized tests love these things, okay? If you've ever taken a standardized test, you've probably seen something like this. They love it. And so the logic behind this is to recognize the pattern and to see what would come next. And very often they'll give you like 4 options, and sometimes it's like they would all work. But they really want the best one. What is the best one that's going on here? So the first one's not very hard, right? The first one you can see you have 1, and then you have 3, right? And then you have 6, and they're forming this triangle. And then you have 10. And so from this particular one, you would gather that the next one's going to be 15, right? They've added 2, then 3, then 4, and then they're adding 5 dots here, and they're keeping it triangular, all right? And so this is an example that's not necessarily numeric in the picture itself, but the process itself was numeric. The next one's not really numeric at all. So you'll notice that we have a circle and a triangle with a solid line, all right? The circle in this one has moved up, and now we have a square and a dashed line. Here, the square has moved up, and we've gone back to the triangle with a solid line. The line's probably easy. What do you think is going to happen with the line itself? It went from solid to dashed to solid. We assume it's going to go to dashed again. What about the figures? Is there any pattern in the figures?
Yeah, but I don't know how to say it.
Right, so we're getting some hand motions back here. So yeah, so they're moving up. So the circle moved up, and then the square moved up, right? And then it's been replaced. It looks like the pattern is going to be circle, square, triangle, and probably in that same pattern again. And so what they have given us here, again, circle, square, triangle. And so that's what we're doing. We're just alternating the triangle, then circle, then square. So we assume it's going to be a triangle, circle, square, triangle. We assume it's going to be a circle. And you notice this is dashed. So this is just an example of one that's not numeric. That's not something you're going to calculate to get. You're actually just going to follow the pattern of what's happening in the picture. They'll also sometimes add a line, right? And you have to figure out where the line's being added, or they'll add a triangle or whatever. And so those are some examples of ones that are not necessarily numeric. All right. The next term they want to talk about is the term counterexample. All right. Counterexample. So if you flip the page of your handout, you have the word counterexample. Is an example which your conjecture is false or incorrect. So in your book, you have the definition: an instance or an example in which the conjecture is incorrect. All right, is an example or an instance which the conjecture is incorrect. This is a way to prove the conjecture false. All right. All you need is one counterexample. So in English, your English teacher may often just warn you about using like all-inclusive words. Everybody does this. All people do that. Nobody does this, right? When you use those types of words, all it takes is one example where that's not true and your statement is false, okay? So, if you say something about everybody does this, then you better be careful because all you need is one example, all right? Kids use this with their parents. You never let me go anywhere, right? All they have to do is give you that one example and, right, your argument is shot because that's not a good argument. If you can provide a counterexample, then your statement is not true, okay? And so what you have to be careful of is when you give me these conjectures, if they are mathematical, you have to be careful that it works all the time. So look at the example they've given you. After examining the listed products, so multiplication, Jennifer concluded that every multiple of 3 is odd. So she's basing it on these examples that she has been given. 3 times 3 is 9. 3 times 9 is 27. 3 times 15 is 45. 3 times 27 is 81. All of the examples that she has been given do provide that answer. The answer is odd. But now she has said all multiples, every single multiple of 3 is odd. What's the problem with that?
30's not odd.
Right, I can produce a multitude, but all I have to do is produce one, right? All I have to do is produce one. No, her conjecture is false. And by just giving that one example, I have shown, no, this is a false statement. And so I have given you a list of 10 conjectures. All right. These are all mathematically based. All right. The only one that I don't think you're going to be able, a couple of them you're not going to be able to do here, and I'm going to give you the ones you will not be able to do here. Number 6, because we have not defined those terms yet. And number 8, we have not defined those terms yet. All right. But everything else is just basic math. Other than 6 and 8, those are terms that you do not know that we're going to learn later. So you can circle those. The other ones, I want you to either tell me if it's true. So examine it to see if it's true. And then if it's false, you need to give me just one example of where it's false. Just one example of where it's false.